Hi, I'm Andrew Gore, and I've got the pleasure of being here with Richard Murray from ORCA Computing.
Thanks, Andrew. Nice to be here.
Great, Richard. So tell us just a brief intro to yourself and that first about who you are and which organization you're in.
Yeah, happy to. Richard Murray, I'm chief exec and co-founder of a company called ORCA Computing, building photonic quantum computers. My background is quite varied. So I started life quantum PhD, science degrees, all of that. Quickly moved into technical consulting. So I spent a number of years working not in quantum, but in sort of business product development. So applying science to new products and processes for some pretty exciting applications and customers. My claim to fame, apart from quantum, is that I helped Oakley look at nanostructured coatings for their sunglasses.
All
So
right, okay.
lots of fun projects like that. I always like to describe that also as the point in my career where I transitioned away from science or pure science towards helping customers apply science, helping to build products using science. And there's a whole art of doing that on the business commercial side, if you like. Then a spell in government or working for Innovate UK. So I was thankful enough in 2013 to be brought in to help run the innovation side of the UK government's £270 million investment in 2013. So really at the dawn of quantum, before really anyone was even considering quantum computing, it was mostly on the sensing and communications side. It was my job to sort of go around and talk to different companies and persuade them to take government investment alongside their own investment into quantum. Then a brief spell at Teledyne, who were doing quantum things, but also for their space imaging division. And then in that spell, got together with Professor Ian Walmsley and Dr. Josh Nunn, who were the other co-founders of ORCA, and frankly got inspired by their approach towards photonics and its application in quantum computing, and started ORCA, and the rest is history.
Right, great. So could we take a step back? About a dozen years ago, I took a bunch of corporate executives to IBM in Silicon Valley on their secret location outside Silicon Valley, and we saw the chandelier for their quantum sort of computing. And they tried to explain it to me about cats in boxes and sort of stuff like that. Now, could you try and give a simple explanation about quantum computing and quantum sort of science for those who just need to understand some of the basics of the theory behind the quantum side of things?
Yeah, I'll do my best. No promises. So let me start with the science side of things, I suppose. So, quantum science is this sort of revolution in science that sort of occurred around 1900s, where people moved beyond believing that everything was deterministic. So pre-1900s, everyone sort of based on sort of thought that Newton's theories were good and proper. Everything is in a hard, well-known place. Everything is sort of well controlled, and therefore you can sort of deterministically predict everything, the universe, everything that happens. Quantum computing or quantum theory was a bit of a curveball that suddenly started to identify certain experiments that sort of didn't fit within that model of the universe. So the idea of single particles passing through two slits at once, the famous Young's double slit experiment, but done with electrons. So they started to discover that there was something strange, unknown going on. Sort of supposedly indivisible particles were, well, the only explanation at the time were being divided to pass through two slits and do other things like this. And at the time, the way to explain it was to imagine that all of these particles were waves. So this is where the famous sort of wave particle duality thing came from, and sort of the layman's way to explain that is that everything that we see around us is both. It is both described by a wave and a particle. And in my view, you shouldn't get too bogged down in the details of that being a contradiction. It just is.
Okay.
So if you all of a sudden imagine these fundamental things being waves, quantum theory emerges, which can describe, again, situations where you thought previously that everything had to be one or the other, and it could not be both or anything in between. So, an electron being in an excited state and the ground state of an atom at the same time, things that supposedly shouldn't be able to happen within quantum theory can happen. So two possibilities, two sort of physical or two scenarios can exist at the same time. And this is at the point where I'm at. I always tell people, if you're sitting there thinking you understand this stuff, you've sort of got it wrong. Like I do fundamentally.
I'm already seeing. You can see by the expression on my face. I'm still curious and haven't quite got it. I'm sure you're going to get to making a point that I sort of see the relevance.
Well, yeah, so I mean, the thing where the point at which it becomes relevant to all of us, I mean, I really count myself as an engineer nowadays, or business person nowadays, was really around the sort of the early sort of 1980s, when several people took that theory and all of the work that had been being done on it and started to relate it to a new theory for computation. So within all of this sort of quantum weirdness, which I don't propose that anyone at this point tries to understand, sort of just trust that several incredibly thoughtful, visionary scientists came up with new protocols, ways to use this quantum theory to perform calculations. And the thing I'll probably leave you with on that side of things is that it's sort of not an incremental improvement in computation. It's a complete reimagination about how you perform computation that takes advantage of the fact that you can sort of hold simultaneously different possible outcomes. So you can test out different scenarios, if you like, or different parameters at the same time. Your quantum state can hold multiple possibilities, you can hold all of those things at the same time, and so you can use those different possibilities within your calculation. So it moves very much away from the try this, if this fails, move on to this, the sort of sequential model of computing to
and I suppose the way I try to get my head around it, after trying to get my head around it for years, is that I don't understand what's happening in our computer here and that at the moment, and how we've got from being able to take a piece of silicon and be able to put lots of on-off switches and that into it, and being able to do these massive calculations. To me, that's wow, that's fantastic. And I've made a career, and lots of people are making, people who are listening to this have made careers out of those technology changes, changing business models and stuff like that. And I suppose my simplistic view now of quantum computing, as you said, is these things can be in lots of different states. So it's not just on and off. And if I replace the on-off switch on that silicon chip with some other sort of fancy computer thing, which can be in all sorts of different states, that moves me from doing lots of on-off switches in my computer to do a calculation, to being able to do it in all sorts of dimensions faster and in multiple sort of times. So that's my sort of explanation of how
exactly
moving that step from the sequential and just binary on-off switches to this quantumy thing, which can be in different states at the same time. So that's my is that a simplistic and clear? Is that a
yes? Yeah, I think that works.
The description.
Absolutely, and remembering that most people working with these things or trying to make use of quantum computing, I mean, it's fascinating to try and understand how it all works. Probably will take you a PhD level study to get to the bottom of. It doesn't really matter. Ultimately, everyone's interested in how you apply these systems, and what you've just said, those models completely relate. They work.
Right. Great. So we've got some sort of understanding that quantum computing is going to be a step change, and it's this down at the very small level. It's going to change from our traditional computing. So what types of business or real world applications should we now start thinking about, in the quantum, how quantum is going to change things?
It's a great question. I always like to describe the ideal quantum calculation, if you could come up with one. You're always looking for areas of calculation that have sort of not a limited number of inputs. So the amount of data you're feeding into your problem isn't vast. The amount of data that you're getting out of your problem, like the ideal solution, again, isn't vast. But in the middle, you have such a number of different complex arrangements of that data that in the middle, you have a vast number of different possibilities. So an example that I often give is, optimizing a network or something like this. It might be very easy to describe the network. So your input data is very simple. It doesn't require a huge amount of data to model that input data. The optimal solution of that network is, again, sort of limited. Isn't that you don't have that many sort of possible so it doesn't take that much data to describe the optimal solution. But in the middle, you have to try and summarize, you have to try and optimize many variations of that network. So input data limited, output data limited, but in the middle, there's such vast complexity that it creates a very challenging computational problem. So that's the general sort of class of problems I tend to try and steer people towards when they're looking at quantum computing. Then we're into the sort of details of things about how big a problem you are trying to solve with your quantum computer. And I will say that, you know, quantum computing is in this really interesting point right now where the number of qubits, the amount of data you can manipulate in a quantum way, it is limited. So even IBM, even sort of world leaders, sort of everyone's hovering around having a few hundred qubits at best. So it's not possible at the moment to run a complete quantum algorithm on a quantum system. So this is where the controversy happens around the field, if I might. I mean, at ORCA, but we believe that it is exciting, fruitful, potentially, to look at what are known as hybrid quantum algorithms, where you solve a lot of your problem on a classical computer. In fact, maybe most of your problem might be solved on an existing CPU or GPU cluster, and a small minority of the problem, the part of the problem which is the most complex, the most hard to solve, is sent across and solved on your quantum machine. So these are what are known as sort of hybrid quantum classical algorithms. And in particular, ORCA's looking at machine learning applications. So ones where you might have a very deep neural network and just one layer in that network might be a quantum layer and the rest is classical. But the reason I say that's controversial is sort of that's a current hugely exciting area of research. No one, I will say, has definitively proven that those applications exist in that regime. At ORCA, we're sort of confident, excited that there are applications for quantum systems in that regime. But you know, we work with different customers, different partners on trying to find them, trying to structure the data so it works.
Okay, so can we untangle a little bit of that? So I'll try and give the simplistic view, probably for people who are trying to listen to that as well. So we use my example of traditional computer jamming, simple on-off switches, and going back to the old pictures we saw when computers were the size of rooms and they were just valves or just some simple sort of switch sort of type things, and never mind kilobytes or megabytes, there was just a few dozen switches and valves that people were using to create the old Turing sort of type computer for solving that. Is quantum computing about that state of development? Yes. It's probably about that sort of state of 1940s Alan Turing doing
exactly stuff
in those on-off switches, and you now are the Alan Turing or whatever in trying to do these qubits, which are those equivalents of those sort of valves and that, I guess, in terms of
that's right. I mean, if you imagine that if you have a few hundred qubit system, you haven't got that many more than a few hundred input parameters to play around with. So initializing your problem is very limited. So you're really looking at, back to your Alan Turing example with valves and things, a very limited amount of data that you can look to process.
Right.
So, again, the thing about quantum is that once you have your 100 or so input parameters and set your problem running, the number of different scenarios that can take is vastly more than the few hundred that you started with. But again, you're reading out a few hundred qubits at the end. So your initial and input and output thing is sort of the order of a few hundred parameters. Okay. So it's sort of not that different exactly from your the original dawn of computing. So where we started off. Okay. With things.
So a business sort of application I've heard talked about within the quantum computing stuff, where you've got a limited number of inputs, limited number of outputs, is sort of within the pharmaceutical development sort of type environment is one example I often sort of think about. And again, if I give you the sort of scenario that I try and picture in my sort of head, is that you've got people in lab coats who are trying to solve for a cell or something in your body of, I've got to try and find the combination of these molecules, these different ingredients that are coming from plants and synthesized in different ways. What's the combination of those things that are going to help this cell grow or help kill it or sort of something like that, in a simplistic pharmaceutical sort of way?
Yeah.
Quantum is that the sort of applications you're thinking about in terms of
Um, so I mean,
complex?
I think we're well, at least in the for our short-term applications, Orca's looking at more simple problems, so sort of more into the traditional sort of machine learning sense. The problem in the pharmaceutical space, as with many of these problems that are purely quantum, is to try and get them to run on the available hardware that we have. So I think it's currently the case that with the current number of qubits, trying to do anything substantial with pharma with those molecules, even though that is the end goal.
That's what we're trying to aim for.
Yeah, I mean that's one of the holy grails of quantum computing when we get there, is to have enough qubits so that you can upload your molecule or whatever it is onto to be represented by the qubits in the machine. That takes quite a number. That takes quite a few qubits, probably beyond what we have today.
Yeah, yeah.
So either you can try and sort of take the whole molecule and try and hone in on the key active region or the part of that molecule that matters. That in itself is a pretty challenging research project. Or you just form a roadmap to sort of see how you can get there. So what many companies are sort of currently forming their roadmap to say, okay, I really need to get this drug or this pharmaceutical or this molecule solved on a quantum computer. Let's do a research project to see what type of resources are needed, and let's sort of chart up. So at least we as a company are prepared for that the arrival of that type of hardware.
Yeah, that's right.
Yeah, mostly it's about sort of trying to understand what you can do today, which is quite limited. It's not I don't believe it's something that would be as revolutionary or disruptive as modeling a molecule. But it might be some part of that molecule, or it might be some algorithm that can apply to the molecule, optimizing some part of it or something.
Yeah.
But then the other part of it is producing that roadmap to see when and where and how your company can take advantage of the hardware once it got to that stage.
Yeah, and I suppose again putting us back into sort of different sort of timeline. I know when I started, doing what I'm doing now, back in 99, 2000, it was like the dot-com era. There were lots of startups doing .com, simple sort of .com online sort of type stuff. But, the corporate that I was working with at the time, I was trouble getting them to look at Netscape, looking at Mosaic, because they know our business is selling direct to retailers, not to, business to business, not to end consumers. And this going direct to consumers. Well, oh no, we don't do that. We don't do that. And I kept screaming at them and saying, no, this is going to come, guys.
Mm.
And I'm sort of seeing now the quantum sort of analogies, I guess, and continuing the pharmaceutical sort of type example, is that we need to change from thinking about traditional computing and people in lab coats mixing things in test tubes, that those things could be done in the computer in future rather than some of the other step changes we've sort of seen in these.
Absolutely. Yeah. And especially, I would say two things. The more a company is at the forefront of current compute methods, and also simultaneously at the same time, the more a company is long term with their roadmaps or thinking, the more that companies really need to start looking today at what quantum is, how it will affect the business, what the future business models might look like. Because take either of those examples, I have the pleasure of speaking to one large financial institution, and this one person mentioned to me that their incoming graduates, they put them on quantum computing courses because in their view, over the course of their career, quantum will become a significant tool that they need to learn how to use.
Yeah.
So and the same might be applied to aerospace, or it might be applied to defense or pharmaceuticals. Pick your largest long-term industry and then imagine how that might change beyond recognition. And that's the type of sort of change which companies can benefit from.
Yeah. And again, putting it back into my timeline, it's the equivalent of giving me the ZX Sinclair computer back in the 1980s or whenever I had sort of, when I first was exposed to computing, it was like, well, you're playing with this thing, which is then going to have the potential to where we're at now, and we're going to have this next sort of thing, and that's quantum.
And the thing about new future business cases, there is this area of this sort of disruptive innovation, which in the technical definition means technologies which you look at first time around and they really don't look very good, and you sort of dismiss them thinking there is no way on earth this needs to be something we consider, like your Netscape or like the internet.
Yeah.
And pretty quickly that gains momentum and becomes a significant driving force in the industry.
Yeah.
And quantum's exactly the same. So it's very limited technology today. You can't do anything that a classical computer can't do. But the fact is that every company needs to get on board and understand what it's good for and what it's not good for. Because otherwise, if there's a 5-year onboarding process, it takes your team 5 years to understand what on earth it is.
Yeah.
And all of a sudden, after 3 years, a huge change in the industry happens and quantum computers are available and become powerful. You want to be that company that's already invested time and effort into building up that team that understands it before it's too late or before your competitor starts to do that. So that's the reason why everyone's so interested in quantum computing today.
Great. So we've got some understanding of quantum computing. We've got some understanding of some of the applications from from the pharmaceutical route planning, advertising, being able to sort of to look at variables and that within there. Now, you touched on when you gave your introduction about yourself about sort of the ecosystem in the UK, for example, with Innovate UK and the initiatives we're doing here. Could you give us a bit of an insight, I suppose, giving ORCA's journey, maybe map out ORCA's journey and how the ecosystem is changing and being impacted by you and vice versa? Because some context of that now.
Great question. So we incorporated in 2019, and so you might say we're a latecomer to the party, but I think we came at it with a completely new technology, a new way of approaching photonics that arisen from research at the University of Oxford. So we came at this with a new quantum memory technology that changed things. We, as a company, very much leveraged the existing photonics supply chain, both in the UK and international. So we quite often work with different partners in the photonics space to say, okay, here's your switch. We need it to be twice as good as it is currently, and we do that type of incremental improvement. I would say as ORCA has grown, as we've matured, we've very much become what's known as full stack. So we have been moving or growing the part of the business in the software application space, because we believe that we really need sort of software and application development to be done alongside hardware development. So in this near-term space, part of the sort of secret of success is to bring those two teams very close together.
Right.
So we now do that, and so now we sort of we don't quite approach sort of the end users, but we approach sort of companies looking at application-specific quantum software. That's a really long way of me saying that ORCA really believes in the community. We believe that this is an industry, sort of a new industry, and that needs new supply chains to be formed, and it needs us as sort of the central pin player in the supply chain to be pulling together software people and hardware people together. And I think this is where I'd say that I think the UK community, having formed so early in 2013, the UK Quantum Programme was the first, I believe, worldwide. Right. has that history, has that already sort of experience of building quantum things to be a great place to be doing that, to be building a new supply chain. Although I will say that the supply chain is global, and I think one of the threats for us all is that it sort of becomes too nationalized by all of these big geopolitical shifts happening. Quantum is a future industry, and industries don't fare so well, particularly large disruptive industries, if they're sort of focused and forced to be constrained within particular geopolitical areas. So that's sort of one thing that we have to keep an eye on, I think.
And we've certainly seen the centres of excellence out of Oxford, Bristol, Cambridge. Those the sort of key centres that you sort of seen.
Yeah, but slowly it's moving out of universities, which is partly the job of ORCA and others. We take some early stage research and we lift that out of the university environment. And then, as Josh, our technical co-founder, says, we put rocket boosters on things. So we say, okay, of all these ideas which make a difference to us, which are the ones that make the most difference, are the most impactful? And then we put significant resources behind those, working with the supply chain to do those really well. So, and I will say, in quantum computing, I think photonics and every other platform is really racing ahead. I mean, really, I do wake up and thinking every day comes with the possibility of a new breakthrough, a new application, or a new hardware step forward. So it's truly And whether that will be within ORCA, one of our supply chain companies, or someone else, I
Yeah,
think is a really exciting time at the moment for all of
yeah.
us.
And when I recently met up with you at a quantum event at the Mansion House in the City of London, seeing that sort of fusion of finance and that ecosystem together was great. And you were very excited about a move that you're now making to your new offices. So
Yeah.
what's the latest news from Walker?
Well, I don't think we've made it public just yet, but we've just moved offices. No, so yeah, we've just moved offices. So we've just expanded our premises. We're now in Paddington, so across the road from Paddington Station.
Yeah.
We've a very now significant office space, but even more exciting, we've just finished the commissioning of our laboratory and assembly facility. So we've now sold a number of our hardware systems. We believe in shipping quantum hardware to customers and who want to have quantum computers on premises. So we've now finished the assembly of, commissioning of these facilities, which allow us to build and deliver quantum hardware to our customers. So, yeah, really exciting time for ORCA. Doesn't give a lot of time for relaxing or sleeping, but
Oh, that's the journey of a startup and a founding CEO and founder like yourself, Richard. So that's great.
Exactly.
Look,
Yeah.
that's been perfect. Thanks so much for tackling you and me trying to explain what quantum computing is, and the you from the science end and us sort of put together around some of the business sort of impact. And thanks for sharing that with our community. Thank you,
No
Richard.
problem. Happy to help.